Okay, off to a somewhat late start. So last week was the first snow day in, I'm trying to remember when the last time it happened. Yeah. It's been a long time, I think.
No, 2 years the year we had, it was like negative 20 degrees or whatever.
Okay.
Yeah. It was like super cold. We had a snow day. Too cold to snow.
Was it a surprise to anybody to have a snow day, or just you expected it?
It was bad outside.
I know. I didn't go outside. I don't have a four-wheel drive anymore. I sold it last year, but I went to school in Upper Michigan, and at Michigan Tech, if you know where that is located. Does anybody know where that's located? Since they play Colorado College in hockey, or at least they used to, it's Upper Michigan has got a peninsula that sticks up. I mean, Upper Michigan sits above Wisconsin. So if Wisconsin's top border is here, Upper Michigan's here, and then there's a peninsula that sticks out into Lake Superior. And that's where Michigan Tech is, because it was a mining school for copper mining up there. And it snowed out all winter long there. 300 inches of snow would just pile up. And they had winter carnival, and they have, hockey, the skiing hill and the cross-country skiing trails, and the rotary snow plows is how they kept the snow going. You know how they use the rotary plows on the passes in Colorado? They used those up there all the time. They were running constantly, and if the snow built up too much in the downtown area, they just took the rotary plows and they'd run down the street and have the dump truck following behind and moving the snow into that, and then hauling the snow out of town to clear the streets. But it was novel, for me at least. Even though I grew up in Wisconsin, there was far more snow up there because Lake Superior provided the water supply to make snow come all the time unless it froze over, which was pretty rare that it would freeze over. So I always think about that, and I thought when I first moved here that this is a wimpy city to, little snowfalls, but then I realized a big city has a problem. They just don't have enough resources to manage all that stuff, and they don't have it in the budget to do all that stuff either. So I understand it, especially as a taxpayer. I mean, it would cost a huge amount of money to have enough equipment to do that sort of job on the streets. So we'll take a look at this eventually, but we're going to move and look at this quiz that I did have prepared. So I'd like to just work through it with your paying attention and giving me some inputs. So I divided it into two sections. I kind of deviated from the original plan because I knew that at the point that I was working on it, namely, when was it? I worked on it in such a way that I knew this probably wasn't going to be a quiz because I just was predicting on Wednesday when the forecast came out and the school campus closed early. So at any rate, this first part is power spectral density. And it's something that we went through a few weeks back when we were looking at the autocorrelation function. But for a sinusoid, you don't have to get the autocorrelation function before you get the power spectral density, if you remember. Formally, you have to be able to get the Fourier transform of Rx of tau to get the power spectral density. But what do you remember about the case of sinusoids and the power spectral density? Remember when we first started going through the power spectrum for a sinusoid, you said that intuitively its spectrum is like its Fourier transform, except that the units work out to be power in watts when you integrate the spectrum. So the amplitudes of the spectral lines are actually the power representation rather than just the voltage representation. Remember that? So what's the total power in a cosine? Amplitude squared over 2, right? So in this case, there's a sinusoid at 200 kilohertz and one at 5 megahertz are the two frequencies that I chose. And the amplitudes are 3 and 5. So the power in those signals is the power in one of them is 3 squared over 2, right?
Yeah.
And the other one is 5 squared over 2. It's just like a side calculation. So if this is going to be the power spectrum, I'm going to let this be S sub x of f and apply the filter second. So if that's the power spectrum of the input, it's going to have some spectral lines in it. And they're going to be located at, like I said, 200 kilohertz and 5 megahertz. So the autocorrelation is actually a cosine wave, if you remember that, but you don't necessarily have to, like I said, take advantage of that. You just know that the power spectrum, when integrated, is the total power. So if the total power of the 200 kilohertz cosine wave is 3 squared over 2, which is 9 halves, what is the power spectrum going to be for that 200 kilohertz wave or signal? Well, when integrated, so this is 9 over 2, right? So you've got to spread that power between the two frequencies. Remember, that's what it was? So it was actually a squared over 4 at the positive frequency and at the negative frequency. Remember that? So a squared over 4 would be 9 quarters. So there's going to be a 9 quarters spike here. And then at the 5 megahertz, there's 25 over 2 is the total power. So there's 25 over 4. And now when you integrate that entire spectrum, spectral density, you get back the total power, which would be 9 halves plus 25 halves. That'd be the total power in that signal.
Sorry, can you repeat that?
The total power, that's not the answer to part B, though. This is just a side calculation. The total power in X is the power in the 200 kilohertz signal plus the power in the 5 megahertz signal.
Okay. So need those amplitudes static?
Yeah, those powers actually. The 9 halves is a power in watts, assuming a 1 ohm impedance, and the 25 halves. Is that right? I mean, is this bringing back your memory? I don't know why my computer's doing that. It makes me think the microphone quit working. But the USB is plugged in, the mouse is plugged in. It might be from undocking it, I hope. Okay, so now there's a filter present in here, and this filter is going to be applied to x of t. So that's an ideal low-pass filter, right? So I need to sketch that filter in. I would sketch it on the S of x spectrum, because this formula says that the power spectral density at the output of a linear time invariant system is the input spectrum times the magnitude squared of the filter's frequency response. So if I sketch that in, where's the cutoff frequency, the filter, where's that at? If it's a rectangle, it has a denominator of 2 times 10 to the 6th. So it cuts off at 1 megahertz. Is that right? Because the full width is 2 megahertz, so it goes 1 megahertz above and 1 megahertz below. This isn't drawn to scale, but it's going to be workable. So there's a filter sitting in here. And the height of the filter, or the gain of the filter, the magnitude squared of the filter gain is what? Well, it's magnitude squared, so it should be 4. So now that filter over that passband and that gain gets applied to the spectrum in blue, and it's going to produce the output spectrum. Which is going to pass a signal and eliminate a signal, right? So the 5 megahertz signal goes away, right? It's gone. So we're just left with the 200 kilohertz signal. But the 200 kilohertz signal is picking up the gain of 4, the power gain of 4. So the 9 quarters becomes a 9.
So how do you determine the magnitude of that thing you was for? Of what filter?
I take the magnitude squared, so then the 4 comes outside, and then the rectangle function is just a switching like function. It just is 1, and 1 squared is 1. Right? If the filter had a shape to it, like a triangle or any other shape, then then there'd be more of an issue. But since it's just 0 or 1, it's easy. And that's, last week when I was talking about ideal filters, remember I said that's why we like to use them in modeling, because they're just simple. They're easy to work with. There's no complexity when you do this sort of a calculation. Okay, so now we have the output spectrum, and now we can get the power in Y by any way you choose, but one way is to just look back in the time domain and say what comes out of there is a cosine, and I can decipher that, or I can just take the power spectral density and integrate it. And I've got 2 delta functions in there, so it should be, when I integrate through the 2 delta functions, I'm going to get integrate the 2 deltas, and each one has area 9, right? So is it 18 or 9? It's 18 because it's the entire spectrum. So this would actually have units of watts. Again, because we automatically assume a 1 ohm impedance level in this calculation. If it had to be done like in the lab or something and it was a 50 ohm impedance level, all you'd have to do is multiply this by 50, because it would just be a change of impedance scaling from 1 ohm to 50 ohm. So you just swap 1, which is sitting in the denominator right now, for 50. And then for those of you in the lab, you'd convert it to dBm. This would be blowing up the spectrum analyzer, though, 18 watts. That would be a little bit too much power for it to handle. If you have to do a measurement like this in the lab, though, you have attenuators, and you can have a high-power RF attenuator sit there and absorb a lot of the power and step it down, like a 20 dB attenuator or greater would step it down. Okay, the second part of the problem, does anybody have any questions before I move on? Second part of the problem related to the idea of distortion in linear time invariant systems. And those were the ideas of amplitude and phase distortion. And then phase distortion can also be interpreted, remember, in terms of group delay. So in this problem, what I did is I just sketched out the gain of a filter and the group delay response of a filter. And then I turned on smoothing in my graphics program, so it rounded the edges, and that's why it's got the rounding on it. But it's still, in my interpretation, it's flat over a band that you can see there. So the first question is, what's the usable bandwidth in the low-pass filter that's free of both amplitude and phase distortion? Okay, minus 30 to 30. Or in terms of a low-pass bandwidth, it goes 0 to some positive number. So that would be 0 to 30. Does everybody understand why that is? The amplitude response is flat out to 50, but the group delay has that peak in it that kicks in at 30 and before it drops off. So I'll just say B sub low pass is 30 megahertz. If you're willing to accept the phase distortion and just wanting to have a flat amplitude distortion, then you can alter this. And that answer would be where the low-pass filter starts to round down. That'd be this point right in there. And if you're not aware of the phase distortion, you'd say, that's good by me. Remember the example I used of the audio filter, where the amplitude response looks flat, but then the phase distortion is getting all messed up by the filter. Pretty straightforward. No tedium. I've got the quizzes to give back, but there was one yet taken today because of the snow from 2 weeks ago, so I'll get those back on Thursday. So before we go back into the chapter, I'm going to take my microphone off for a second because I'm starting to roast with my shirt on. Before we go back into the com theory part, I just want to point out some things that I posted on the website today, if the web browser will open up for me. It might not. So I posted the first computer project, which is based on single sideband, and that's down in here. And it's a project that you can work on with a team of 2. So you can pair up to work on this project. And it's got a zip package that goes with it that has some code base in it, and the document itself, which is got a lot of writing in it, block diagrams and things of that sort. I think I might have it to pop up on the screen here too. But the other thing that I went and did, was I posted 2 old exams. And looking at the dates of these old exams, they were given like on March 7th and March 8th in those 2 years of 2007 and 2012. So if I go over here and look at the calendar, and I say, when should we have our first exam? I look through here and I say, we're about ready to enter into March. And so I say I could put it on the 7th, or I could put it on the 12th. So those are the days that I'm thinking of right now. I'm leaning towards the 12th to give a little bit more time for things to settle, but I can't procrastinate too long. If you're in senior design, you know that that's also the week of the design review.
I still vote for 12.
We'll talk about it again on Thursday, but I thought I'd get the discussion going, and there's a couple of people that aren't here today for reasons that at least one person sent me an excuse. So you can look at these old exams. The 2007 exam tended to be more focused on Chapter 2 review and touched very little on the com theory Chapter 3, whereas last year's exam tended to be more on the com theory, but not 50%, but it just had more. So I don't know exactly what was going on. I do think that we're running later this compared to last year. I think we get out a week later in May than we did last year. So I don't think it's like we're in trouble or anything. It's just the way the calendar is set up. Does anybody notice that from last year?
Yeah.
It's like we're a week later, aren't we?
It feels like
I haven't really counted the weeks, but I know spring break is at the same time, so it must mean that we have one more week after spring break than we did last year. But I don't know. I haven't studied it close enough, but not that it really matters. So I'll go into chapter 3. And I'll give you some overview of the project next time. Hopefully you'll get it off the website and you'll take a look at it and be ready to. It relies on single sideband, so we have to get into single sideband, and that hopefully is going to happen on Thursday. So last time I just briefly started this chapter. What I said was that with modulation theory, and this is linear modulation theory, we generally want to locate a message signal, and this is Dr. Ziemer's terminology in the book, message signal. And message signal for now is going to be an analog type message, but it could be a digital message. It could be ones and zeros. The major focus in this chapter is analog messages, and digital messages comes near the end. So you've got a waveform that can have a carrier frequency FC. So that can locate the information centered up on a carrier frequency. And then you have choices, and the choices that we will mostly focus on in the first part of this chapter is linear modulation, which is A of t. That's the first thing we'll look at. And then phase modulation, which goes inside the cosine and messes around in there, basically. In 2610, if you can think back that far, do you remember the lab experiments with the bell tones? Do you remember looking at the spectrogram? Some of those things? Those were, in the instantaneous frequency, those were examples where this is the type of modulation going on. There was actually a part of one of those labs that said frequency modulation, I think. Or at least when I teach it, I use that lab. You might have not used that lab when you had it. So this is going to wrap around onto that. When you had that lab, you didn't know the math. It wasn't possible to understand it, but when we get to it here, it'll be possible because of the math we're going to go through to understand what's going on. Linear modulation, though, is less complicated to understand. So we'll take and do that first. So without loss of generality, as the mathematicians like to say, I'm going to set phi of t equal to 0 for the time being in the transmitted signal, and just transmit this signal on a carrier frequency of fc. And carrier is appropriate here because it's the RF signal that can propagate through free space, being launched off an antenna and being intercepted at the other end with an antenna. And I know when you take EMAG 1, you study a little bit about antennas in that class, right? It's a structure for, well, what's something that I think you probably learned in that class? Did you learn about reciprocity?
not there yet.
Okay. Well, the idea of an antenna is that the pattern that it radiates is identical to the pattern that it receives with. So it's reciprocal in nature. It does, you know, if it radiates in a certain pattern, it has that exact same gain pattern as to how it receives. And the way I like to think about antennas, and we'll look at this later on, is you're radiating so much power, like if you put a power meter on the line of this signal, we know for an unmodulated carrier, it's just the amplitude squared over 2. That's how many watts are going out. So when it leaves the antenna, it gets spread out into watts per meter squared, so it's like a flux density. And then the antenna at the other end has got an effective aperture area, kind of like a net. And the net has so much area, so it's got so many meters squared of capture area. And you've got a flux density that hits that, so it converts the watts per meter squared through the aperture area back to power. That's sort of the simple-minded view. So we have to be able to capture enough power to be above the noise floor, and that's what we'll look at in the appendix late in the semester, to have a good enough quality signal for demodulating it and recovering the information. So amplitude modulation or linear modulation puts the message signal proportional to A of t, and is in fact, as we start here, it's direct, it's just equal to it. Rather than being proportional, it's actually equal to it. So we have a carrier amplitude and an m of t, and if you Fourier transform that as a result of the modulation theorem, you get the spectrum of the transmitted signal is the spectrum of the modulation. So this m of f, I didn't write it out, is just the Fourier transform of m of t. You get that spectrum shifted up in frequency and down in frequency, and then you get these 1/2 factors from the trig Euler's identity. I mean, when you expand cosine out, you get a complex exponential that's positive spinning and negative spinning with a 1/2, right? Remember, this was called the modulation theorem, so that's why the 1/2 is on there. In terms of the time domain, if m of t happens to be the waveform that is the message signal, then you multiply that times the high frequency carrier. It'll have this sort of a picture to it. Now, if you were to try to look on the oscilloscope, which is something that you try to do in the lab or will do in the lab, the cycles of the carrier are typically so much higher in frequency than the message signal itself that it's just blurred. It's just filled in solid with whatever color the display is. But if you were able to sync on the message signal, like I've drawn this picture here, you can see that it has an envelope pattern that follows the message signal. And because the message signal multiplies the carrier directly, each cycle of the carrier could be positive and swing negative, so it's folded onto itself, like it's shown in the picture there. That's not an error in the drawing. It's because cosine can take on positive, negative values, so it takes each amplitude value and it flips it, makes it alternate back and forth like that as the cosine cycles take on positive and negative values. If you look at it in the frequency domain and you were to say the message is a band-limited spectrum, this triangle centered on 0, then, like when we looked at the modulation theorem, we were shifting it up in frequency and down in frequency, and there's a 1/2 factor on there. And it's customary in modulation theory to talk about the spectrum just on the positive frequencies for a moment and say that there's two sidebands here. There's the copy that sits above the carrier is called the upper sideband, and the copy that sits below the carrier is called the lower sideband. And this is true of virtually all modulations unless it's single sideband, in which case then it's not going to be symmetrical. But remember, the symmetry comes about because we started off down here with a real signal. The real signal has magnitude of its Fourier transform being even. And I'm not really that concerned about the phase spectrum, so I'm just thinking of the magnitude spectrum, or a spectrum that has 0 phase. So it has a like piece of spectrum that sits above 0 and like piece of spectrum that sits below 0, so when you shift it up in frequency, it becomes what's called the upper and the lower sideband. Make sense? And the thing that we're also going to notice here, if this happens to be a bandwidth W, then this is going to be Fc plus W, and this is going to be Fc minus W. So the total bandwidth occupied by this signal on the carrier is 2W, which is the way it is, but if you think about it, you'd say there's an inefficiency there. We're taking twice as much bandwidth to send this thing on a carrier as it requires down at baseband if we were just sending it through some speaker wires, let's say, through your earphones to listen to that signal, for example. So that's the innovation that single sideband has with it, is it's a mathematical representation that eliminates one of the two sidebands and only takes half as much bandwidth. And there's other schemes out there that can be bandwidth efficient, but bandwidth efficiency is subject to interpretation in applications. You get robustness in the signal if you occupy a lot of bandwidth, which makes it more immune to interference and jamming and noise. Whereas if you have it lean and mean, then it's more subject to noise and interference. So it's just a trade-off. You can't get something for nothing in terms of communications capabilities. In the military, most of the time has preferred to go with lots of bandwidth with spread spectrum so that you can be secure. Like military SATCOM, for example, will use spread spectrum almost all the time. Spread the signal out so it's more robust for interference and jamming. Cellular, we tend to spread it out so we can all use the same cell and not interfere with each other. Okay, the name of the game with communications, though, once you get the signal up there and modulated onto the carrier, you've got it at a high enough frequency that it's easy to propagate it from point A to point B. You can use small antennas, you can take advantage of the propagation characteristics of the channel and so on. But now at the receiving end, you need to get the message back again. So this simple linear modulation has a very simple demodulator. And the idea is to come along after it's gone through the channel, which is, this is an ideal channel, I'm going to say. So the received signal at the receiver antenna matches the transmitted signal. I'm going to come along and multiply the signal by 2 cosine of 2 pi FCT. And then I'm going to apply a low-pass filter. So the demodulator consists of, if I was drawing my block diagram, it's these two blocks. This right here, y sub d of t, is the book's notation for demodulator output, and it's approximately going to recover m of t. If this seems simple, it is simple, but there's one really important catch which we're going to be looking at, and that is that signal. That signal right now is what's called a coherent carrier. It's exactly at the proper frequency of the signal as it arrived at the receiver, and it's exactly at a phase of 0 to match the way it was transmitted. So I go through the math model here and I multiply that received signal by this coherent carrier. I can then take the trig identity for the cosine times cosine, which is going to be the 2 cosine squared of x, which is 1 plus cosine of 2x. So it's the first term in the trig identity, the 1, just produces what we started with, AC times m of t. And then the second term is the modulated signal all over again, but it's at what frequency? What's in there? It's at twice. It's at the double frequency, or 2 times FC. If you look at the time domain plot, it looks like this. You see the original signal looking fairly good, but then you see a double frequency carrier term filled in between. At least that's what I'm telling you, that stuff is in there. And this is what it looks like in the frequency domain. So you've got a copy of the signal back at baseband again, and then you've got the spectrum of the signal at the double carrier frequency, 2FC and minus 2FC. So to get back what you started with, that's where the low-pass filter comes in. Just envision an ideal low-pass filter whose cutoff frequency FC, or F low-pass, is greater than W, and it has to be less than what? This is going to be 2FC minus W, right? Get quite a bit of slop in there, but guess what? You can't build the ideal low-pass filter, so you build it fairly close to W and then have it sloping off with its stop band or its transition band to try to get a lot of attenuation of the double frequency term. Looks pretty nice and slick. In the real receiver, you'll have gain fluctuations because the signal amplitude goes up and down as you get further away from the transmitter. So you manage that with something called an automatic gain control, something that levels the gain out depending upon signal strength. And an AGC is a control system loop, actually. It has a feedback in it, and it monitors the power and regulates it to hold it constant. So these bullets we're talking about the cutoff frequency, but this is kind of the big stumbling block. We had this, what I'll call a magic genie signal that is sitting there at the receiver. It's exactly at the frequency to transmit carrier and exactly at the right phase. How can you do that? Take two generators in the lab if you've ever tried this, and you guys in the comm lab experiments will be playing around with things like this. They're going to have a slight difference in frequency even though they're synthesized sources. But then if there's motion involved, there'll be Doppler shifts, so then that'll induce more factors. And then just the fact that they're separated in space, what also happens? You get a phase shift, right? Because time delay is equivalent to a phase shift. So what comm systems engineers do is they'll say, okay, we just proved that the idea works if we have this ideal coherent reference, right on frequency and zero phase. Let's perturb the receiver and make it more realistic, and suppose that we can get the frequency right on, but now we're going to have this time varying phase, and see what happens if we throw that into our demodulator and rework the analysis with the non-coherent carrier in the receiver. So now it comes out that the double frequency term again is going to let's see, I've got something not right in here. I'm missing a 2, what I think I'm missing. Just got to go back to my labels. Yeah, D of T is after the multiplier, so I've got a typo in here. This should be 2 times FC. So that term goes to 0 down in here because the low-pass filter removes it. But now we have the message multiplied times cosine of theta t. So if theta of t is a constant, it doesn't look too bad as long as theta is not equal to pi over 2 or minus pi over 2, because then it's going to totally annihilate the signal, right? It would be 0. But if it's slowly varying, if we go up to the math model from the modulation theorem and suppose that theta of t is just a slowly varying term that corresponds to a small frequency error, and that's fine because theta of t could be delta of f times t, where delta f is a frequency error. Go through the modulation theorem or go through the trig identity, and we're basically seeing that now we're going to get, for the tone modulation, we're going to, if we had a single tone for the message, we're going to get that message at FM lowered by delta F and also raised by delta F. Now that's not all that great because we hear the tone superimposed with an upshifted and downshifted tone, and that's what I'm going to demo for you right now. If it's a single tone like that, it kind of sounds like some discordant sound, but if it's speech, I'm going to demo that, it sounds pretty awful. It's not totally unintelligible, but it's not acceptable. If the message instead was digital data, it would be impossible to recover the bits because they'd be all scrambled up. So we'll talk about ways of recovering the carrier, but first let's do this demo. These speech files you see over here in MATLAB are speech files you're going to be able to play with in the project number 1. I got them from a speech file warehouse on the internet. And the one I loaded in before class was this UK version. So it's British male. There's a American male and an American female. And why do they have all these different variants? It's because when they test speech vocoders, which are used in cellular telephony, remember I told you how it's synthetic speech, they have these different libraries because they have to see, does it work with a female voice, does it work with a male voice, does it work with a child's voice, and so on. So they have different libraries of voices up there just to do experiments with. So I'll play to you what this one is, if it's still in here. So I'll use the sound function, and I'm not going to play the whole record, I'm just going to play part of it, and it was called data when I imported it.
The little tales they tell are false. The door was barred, locked, and bolted as well. Ripe pears are fit for...
So all of these files are just people reading little poems out of books and things. So you'll be playing with these in the project. There's different books they're reading from. I've been using them a lot over the years, so I'm used to some of them. So that's the British one. So what I did is I multiplied it times a cosine at 100 hertz. And these sound files were sampled at 8,000 hertz. So they're 8 kilosample per second speech files. So I shifted it up by 100 hertz. So I said there was a frequency error of 100 hertz. Okay? So I multiplied that together, and it became Y. So this is, remember the spectrum was sending at baseband, but now if I shifted it, if I have a 100 hertz frequency area, I have a copy shifted up by 100 and the same copy shifted down and then superimposed. So we're listening to the speech itself shifted by 100 and shifted down and then superimposed.
The little tales they tell are false. The door was barred, locked, and bolted as well. Ripe pears are fit for...
It's understandable, right? But what happens if I lower this frequency? So instead of being 100 hertz, how about 10 hertz?
The little tales they tell are false.
So that's not too bad either.
The door was barred, locked...
It's kind of fluttering in is what it should be doing.
Ripe pears are fit for...
But if I lower it down even more, make it really, really slow, like maybe, I don't know, half a hertz. So it actually is like going up, it's like the volume is going to be going up and down is what it should be sounding like, a little bit. I didn't try this before class, so I don't know what it's going to sound like.
The little tales they tell are false. The door was barred, locked, and bolted as well.
See, it's fluttering up and down.
Ripe pears are fit for...
And if I went even slower still, like 0.1,
The little tales they tell are false. The door was barred, locked, and bolted as well.
so if it was really slow and you couldn't get the phase right, it'd be like the signal would go away and then it might come back again, but it would have a really slow rising and falling in amplitude because the phase, pardon me?
Why is it doing that?
Well, that's a good question. You have to go look at the math. So we're talking about this guy right here being a 0.1 hertz sinusoid, and it's so you can think of that as it's swinging between -1 slowly to 0 and then to +1. So if the signal gets phased by 180 degrees, in other words multiplied by 1 or -1, our ears can handle that phase flipping okay. You don't really notice that much in the phase flipping, but when it goes through 0 and as it hangs there, it's like turning the volume down to 0, then bringing it back up again, then it comes back down to 0 and goes away and then comes back again. But when it's going faster up and down, or the frequency is faster, the COM theory analysis tells us that message signal would be like this sinusoid. It's going to be superimposed with itself, and that's what we were hearing at the higher frequency, where it sounded like it was ringing, like you were hearing the speech shifted up and shifted down and then superimposed. So it's like harmonizing with itself, but it's not harmonizing in a pleasant way. It's kind of a discordant sound. Does anybody ever listen to amateur radio? It sounds a little bit, this is what it sounds like. Except single sideband is what amateur radio people favor. So you will be doing that in the project. Any questions, or did you hear enough? Understand, though, if it was digital data, it would be very hard to recover the data. As a matter of fact, you can't. Because if you're flipping phases, basically the data that would be modulated onto the carrier, and I'm thinking of just directly modulating a 0-1 pattern, which would be shifted to plus and minus ones, and then it becomes what's called binary phase shift keying. That's the very simple digital modulation. Flipping the phase like that would flip the polarity of the bits. So the bits would be right side up, and then they would shrink down to 0, and then they would flip. And how are you going to cope with that? I mean, you could handle an inversion of the bits if they would stay put, but if they're going along in one polarity, then the whole pattern inverts. You can't keep up with that. I mean, normally in digital communications you have what's called an ambiguity, and you can deal with that by having a pattern embedded in there, or using differential decoding and differential encoding, and then you can unravel the phase ambiguity. But if it's constantly changing, it's like you get a few good bits, and then you'll get messed up, and then you'll get a few more good bits. You'll have to resend the message. So you need a coherent carrier.
So when you have the signal being multiplied by phase, was that some mathematical manipulation? You have your carrier signal with some additional phase added on, but you have to transform that trigonometrically to get it into just a multiplied by cosine theta?
It came about because we said, from a modeling standpoint, right here, I said, let's pretend that the reference carrier in the demodulator is now got that theta of t as a perturbation from what it was transmitted with. It was transmitted using just 2 pi fct, but now we're saying at the receiver you don't have perfect knowledge of what the transmitter did, or your oscillator is drifting relative to the transmitted one, or there's motion involved, so there's Doppler.
They're not the same.
Yeah, you just can't hold them the same. And you guys are somewhat spoiled because all the function generators that you've used in the lab are synthesizers. So they have a quartz crystal at a high frequency divided down to create a pretty accurate frequency. When you dial a frequency in on the generator and it says 1 kilohertz, you can set quite a few decimal places on that. If you went back in time where the function generator was an analog function generator, you would turn the knob, and if you had another generator right next to it and you tried to set it at the same frequency, you'd mess with those knobs, and you'd find the knobs would have backlash in them. So you'd turn the knob and that would kind of spring back. You'd try to get them right on. You would never get them to stand still because they're just not that stable. And the higher frequency you go, the less stability there is. There's, even with a synthesizer at microwave frequency, there's still going to be hertz or kilohertz of frequency error involved as they drift and as they age, or temperature sensitivities too.
So to get that from that carrier signal, did you transform it into 2 different cosines multiplied together in order to get down to where you have y and b equals mt cosine theta?
Yeah, okay. What I did, and I was missing the 2 in here, I took the original signal, which was AC m of t times cosine 2 pi fc of t, and I multiplied that times c of t.
Okay.
And then from the trig identity, I have the 2 terms. I mean, there was a 2 in here, right? So that takes care of the 1/2 from the trig identity. And now I get the sum and difference just like I did before. The difference just gives me the cosine theta, which before that gave me the cosine of 0, which was 1. And the sum,
Okay, so so it comes
this
from
is the sum, comes from the difference term.
Okay, so it's just the sum of difference.
Yeah.
Okay.
In Lab 3, you'll start playing with this, with the multiplier and stuff, and you'll see both pieces on the spectrum analyzer, and you'll be shooting to recover the difference term. But the generators in the lab, even if you use a different generator for the demodulator, they're so stable, and you can dial the frequencies in so closely that it will sound really good. You won't notice it being that bad. But if I'm doing something with the real-time DSP class, for example, there's a crystal oscillator on the board for the clock that forms the sampling rate clock, and if I have everything run off of that clock between two different boards, they're sliding past each other because there's frequency error in the crystals. And if you try to do this sort of operation, you will not get satisfactory results. That's a good question. So one scheme to try to resolve that at the receiver is this idea here, where I come along and I square the signal. So this is the received signal path right here that I was using before, but I'm going to tap off from that and come up with some scheme that's going to try to recover the carrier. So this is called carrier recovery in general, and it's popular in digital communications because you absolutely have to have it there. So I could square the signal, and if I square the signal, I'm going to have, assuming that there's a non-zero DC value when I square a signal, and just think about a cosine wave. If I square a cosine wave, I get 1/2 plus 1/2 cosine of twice the frequency. So that 1/2 is the DC, or related to the power in the signal. So if I have that signal with the modulation on it and square it, I will also get the spectrum of the modulation convolved, right? Because when I multiply signal times itself in the time domain, I do convolution in the frequency domain. So that green blob there is the spectrum of the message convolved with itself. And then the spectral line is popping up because of the DC component that's in m squared of t. In other words, what I'm saying is the spectrum of the Fourier transform of m squared of t, I'm saying that is going to be m of f convolved with m of f, and I'm hypothesizing that there is going to be a DC component that comes out of or there's going to be a DC component that comes out of that, which is going to give me that delta function. Plus, over here, these are the other terms that they contribute to that smooth shape down in there. But it's the delta function that I'm looking for. And if I can put a narrow bandpass filter around that delta function, then hopefully I can get just a pure sinusoid at 2 times FC with a narrow enough filter, and then I could put it through a high-speed comparator. This is hypothesizing a bit, and then I could divide that by 2, and then I could get back to a cosine wave from a square wave back to a signal then that I could use to demodulate. There's a bunch of ifs in there. Actually, a phase-locked loop is what we need, and we'll be talking about phase-locked loops later in the class, but that'd be a way of getting a carrier right off of the signal, because there is no carrier present in double sideband. Double sideband is what's known as a suppressed carrier scheme. It does not have a carrier spike sticking up above the message signal. The message was just shifted up and shifted down, but there's no spike sitting up. My finger is supposed to represent the spikes. If there was a pure carrier component, then you could recover it and use that to demodulate. But right now, with what we've been looking at, that's not possible. Is that making sense?
So you can't do this with the double.
Oh, what I proposed in the block diagram is a way to do it, to recover it if there's no carrier present. This is a way of regenerating. So So it's a carrier recovery concept.
Okay.
So the idea here was to
So, are you basically just squaring it so that most of the content of the signal gets more centered and then doing the bandpass filter?
I'm squaring it because I know that when I square a signal, I'm going to be squaring the message in particular.
Right.
And then I think of the filter as acting like an averaging device. In other words, if I was to just do this, m squared of t, and remember the notation for time average is that, that should give me the power in the signal, right? So I'm assuming the signal has a non-zero power, and the cosine, which is multiplied times that, just shifts the whole thing up to the double frequency. But then I'm recovering the power in m of t times the cosine of the double frequency, and that's what my picture is down below. This is supposed to be, this is a little bit wrong here. That's supposed to be the spectrum of m squared of t times cosine squared of 2 pi fct. Got a typo in there. The cosine squared just gives me, the upshift and the downshift in frequency. But I'm looking to get something that can be tracking the carrier at the input. In this case, it'll be at twice the carrier frequency, but I can divide it down or use a phase-locked loop setup. We'll look at this when we look at phase-locked loops. There's a technique called a Costas loop, which is pretty popular for carrier recovery.
So does squaring that just give the message more content than
It's trying to transform it in such a way that we can get a spectral line generated at 2fc. It's a nonlinear processing scheme. Notice it's in the lower path. I'm not going to use the squared message to recover the message, because that's, squaring the message is going to destroy its integrity. But I'm using it in that lower path as a means to derive a coherent carrier from the signal that doesn't have a carrier obvious in it, because it's suppressed carrier. What I'm meaning when I say suppressed carrier is back over here in the very beginning, when I just multiplied, there's no pure carrier term present here. Yeah.
When you said if there's not a strong carrier present, so what they do is what they do sometimes is, like, the signal that they modulate your message with, they also said that they could just add the cosine at that frequency, add it, and then have that spike be above your message signal.
Yep, that's on the next page of the notes. Thank you for the segue. Yeah, it's called carrier reinsertion, or not carrier reinsertion, it's called a residual carrier. Putting that in the waveform, which aids the receiver then, because right now this receiver needs help if it's going to be able to recover the message. It needs to have a coherent carrier. So here you can add in a small amount of unmodulated carrier, and that's exactly what you were visualizing, right? See the red spike there? That's adding some residual carrier in, and then you can use either a narrow bandpass filter to try to track it, or a phase-locked loop can do that. And then you can demodulate. But still, it's a little bit tricky to make this work. And the downside of this is the total power in the transmitted signal is now going to be the power in the sidebands, upper and lower sidebands, plus the power in that spike at FC. So you're going to be putting a certain amount of transmitted power just into that residual carrier to make life easier for the receiver, but that's going to require power be allocated just for that purpose alone, and it doesn't, it's kind of wasteful in a way, but in a way it's not wasteful. I mean, if you have to have the coherent carrier to demodulate it, it's worth putting some power into it, but how much is how much.
Are there other ways to do it besides this method?
Well, amplitude modulation takes it to the extreme of just putting in a huge amount of power, and then the receiver is trivial at that point. You have to think about the economics, though. Amplitude modulation, which is used for talk radio, there's one transmitter and many, many listeners. So the economics there is, let's make the receivers cheap so that everyone can own one, and the transmitter just has to broadcast more power, but that's okay. Whereas in the other scenario, if there's not very many receivers, you might go through all the trouble to build the coherent demodulator, because that's more efficient use of resources in the long run. And SATCOM, for example, will typically do it that way. But commercial broadcasting won't. AM radio, which is now talk radio pretty much, is the oldest form of commercial radio out there. I mean, it followed Morse code and other things like that, but it's been around for a long time.
And when you do the residual carrier thing, do you lose information at the center of your...
Not really, but if there's if information is allowed to be in the message, right down, say in there, if you don't carve a little piece of the, at least reduce the amplitude of the message signal close in to DC on the message or close into the carrier when modulated, then that those pieces of information in your message will perturb the ability to recover the carrier to do the coherent demodulation. So you may have to limit it. It would be like in a music type message, it might mean that you won't allow any content below a few hundred hertz, or maybe even higher than that, maybe up to a kilohertz or so. In satellite communications, when it's digital information being sent, that content in the spectrum comes about because you have long strings of ones and zeros. That would fill the spectrum in down at DC a lot if you have a long string of ones and zeros. Does that make sense? Very little change, so it occupies the spectrum at a low frequency. What they do in digital comm is they'll put scramblers in there to make sure that long strings of ones and zeros are broken up, that they can't occur. That's done on purpose because the synchronizer circuits start to get confused if the data is having spectral energy close to the carrier that you're trying to recover. Okay, amplitude modulation, like I said, just avoids this altogether, and it says let's just add in a DC bias onto the message. So they're going to have a bias plus the message. So that ensures that you've got, effectively, when you normalize it, you've got 1 times the carrier plus what's called the modulation index A times the normalized message. And the message is normalized so that its negative value never goes below -1 when it's normalized. And then the modulation index is a scale factor that runs typically between 0 and 1. And 1 corresponds to 100% modulation index, which you'll see in the lab generators when you work with those in the lab. So what that waveform looks like with the bias on there, rather than the envelope crossing through itself like it did for the double sideband, it stays above the axes, so it never crosses through amplitude of 0, as long as the modulation index is less than 1. So that's how you generate the AM, by adding the bias term on and then multiplying that sum by the carrier frequency. Now what's really nice about AM modulation, and I know I'm running out of time, is that to demodulate it, all you have to do is send it through a half-wave rectifier, which is going to pull my audio out so I don't hear that anymore. And then you can just low-pass filter the top half of that waveform, and you've got your message back again. And that's this picture right here. So a diode, a resistor, and a capacitor is all you need to recover amplitude modulation.
So the diode brings it back down to being
The-
halfway rectified.
Yeah, half wave rectified, that just keeps the positive half, right? I'm using a simple electronics model, just thinking of the diode as a switch. If it's positively biased, it's on. If it's negatively biased, it's off. So it's passing the positive half. And then you just filter it. And I have a little simulation that I did in a SPICE simulator a while ago that just shows what happens if you put some capacitor in parallel with the resistor. I had a 1 nanofarad and then a 10 nanofarad, or 10 microfarad, I guess it was. So 1 nanofarad didn't do hardly anything with this carrier frequency. I don't remember what it was. It was 10 kilohertz in this model. But then with the 10 microfarad, it took it down pretty good. Normally the carrier frequency is pretty high so that it's easier to get rid of the carrier frequency. And we'll see how that comes about when we look at the superheterodyne and intermediate frequencies and some of these other ideas that are coming up here in a bit as well. So this is what made radio come into being back early in the last century. Cheap receivers. I mean, this is what makes the crystal radio work that you can buy at Radio Shack without any batteries, because you just put a long wire antenna on it, basically have this inductor sitting over here, and then you have a capacitor that forms a tank circuit and a long wire. So you have some resonance at the carrier frequency by tuning the capacitor, let's say, and you get enough amplitude because you make this be a Schottky barrier diode, or in the beginning this would be like a germanium PN junction as opposed to a silicon PN junction. And I'm not semiconductor devices, but something that has a low turn-on voltage. A Schottky barrier diode would have a turn-on voltage of like 0.2 volts, as I remember. What do you guys know about that type of diode? It's less than silicon though, right? Silicon is 0.7. So you get enough amplitude across there, and then you can receive radio stations just by putting an earphone on over here. It's not very high quality because you can't select the stations very well with that single resonant circuit, but it works with no batteries. If you have never done this, think about it sometime or another, because it's intriguing if you're interested in communications theory, how simple it is. And you'll hear talk radio, because that's all that's on, right? Sports and radio talk shows.
So, Dr. Worker, was what we just talked about before, was that frequency modulation?
No, that was double sideband, suppressed carrier, just double sideband. Usually it's called DSB in the book, double sideband modulation.
Okay.
And now we moved into amplitude modulation, which modifies the whole scheme by throwing in this bias term. And then that allows that envelope to open up, separate. You know, what we had initially was the envelope was crossing through itself. But by taking and applying the bias term, it's like pulling it apart. So now you don't have the valleys in this envelope crossing each other. And now the envelope detector can come in there and strip off the positive half. The limitation is this has to be greater than, say, 0.7 if it's a silicon diode. And in the comm lab, that's what you're going to be using, is a little 1N 4148 glass bead-looking silicon diode. But then I suggest in there that you can build something called a super diode using an op-amp, which, did you learn about those in electronics? And then that lowers the turn-on voltage, so it makes it easier. So, any questions on that?
So it still uses the, I mean, so all these modulations that we're going to be covering are still going to use that carrier frequency?
Mm-hmm.
It's just different.
There will be some baseband. We'll look at pulse width modulation. We'll look at pulse position modulation. But those aren't, and pulse amplitude modulation, those aren't really all that popular. Pulse width modulation is pretty much used for motor control. But it is used in, it could be used in the Class D amplifier type stuff, right? That Robert's doing for his project. So we'll look at, those get looked at later. But right now it's angle modulation, which we'll get to, and linear modulation. So I think I'm about out of time. I'm going to come back and look at some of these things next time, thinking what else do I have up here. So when you do AM modulation, one of the really bad things about it is that you've got this pure carrier. So if you look at the spectrum of it, you have the message shifted up and shifted down, which says it contains as a subset double sideband, and then it has pure carrier thrown in, and the pure carrier is pretty much a luxury. The luxury is it allows for easy demodulation. But if you go look at the efficiency and go through the analysis, which we'll spend more time on next time, you come up with this formula which says that the efficiency of AM, the amount of power that's in the sidebands over the total power, is typically very, very low. A little example here with a modulation index of 0.8, 1,000 watts of total power being transmitted. We go look at this, and this is the way some of the homework problems work out. There's 757 watts of that 1,000 total power is just in the carrier alone, and 242 is in the sidebands, and that's what you use to recover your message. So it's only 24% efficient.
So the idea is to be able to demodulate it easy enough without spending a lot of power.
And yeah, so that everybody can own a receiver. And that was kind of the beginnings of radio broadcasting. But it comes at a huge price. So the AM broadcast towers, which are here, some are located around out in the plains as well, are doing that type of broadcasting. So they're blowing your brains out with carrier power just so your receiver can be simple. Have you ever seen antenna arrays where if you're looking down on the top you see like 4 towers in a row? Have you ever noticed those around? Like when you drive up to Boulder or something, I think there's a few up there. Those are actually vertical dipoles. So it's a half of the dipole is sticking above ground, and then image theory says it's underground, but those are phased. So if you're looking down on these, it's a phased array of 4 elements, and it's trying to form a beam pattern that might be, this main load beam is to send all the power, say, to a city, and then the phasing is such that it's not going to send it in that direction or that direction because interference. Those are giant phased array antennas for AM broadcast because it's at such a low frequency. That's why they're so far apart. They're huge. You think of a little antenna for a cell phone. This is a monster antenna because it's not just one pole. It's spread out, but it's only at a megahertz, so you need a lot of spacing.
So the idea is to try and prevent destructive interference, so that's why they have an array, so that you don't miss it.
Well, constructive and destructive, so you focus the energy in one direction and then you null it in other directions.
Okay. Yeah.
Like send it to Pueblo, but don't send it to Colorado Springs, or vice versa. I mean, that's just for frequency reuse. Remember we talked about that when we were looking at the spectrum? Or at least I thought we did, but maybe it's in my imagination. It's in my book as a sidebar because I get into that frequency reuse. Remember we talked about Monument Hill FM stations transitioning as you go over the hill?
Are we going to have a quiz on Thursday?
Yeah.
Over what?
So the quiz will be looking at some calculations with amplitude modulation. I think what I'm going to have to do is I'm going to have to put up the solutions for the homework, and I will pick a couple of example problems that are based on the stuff we talked about today. So you'll have to be diligent and go look at it. Don't look at it until late tonight or early tomorrow because I've got class after this, but I'll put up the solutions and then I will make notes on what exactly. I'll say like 3B, 4C, or whatever. Keep it within the scope.
What problems to focus on.
Exactly.